My name is Sri Ilaprolu. I'm part of AWS Public Sector team. My role here is to introduce our guest speakers here. So we have two speakers from NYU, Harish, who's an assistant research professor at NYU, as well as Fernando, who's a research student or a PhD student at NYU. They're going to be talking a little bit about the effort and the project and the research activity that they're conducting, which deals with taking disparate data sources that are time series based in an urban setting, aggregating that data, analyzing that data, and extracting valuable insights based off of that data. And when it comes to doing it on premise, it's well and good, but when you think about aggregating lots and lots of data, it becomes a little bit more challenging, and that's where they're doing experimentation in terms of scaling, leveraging cloud resources. So without any additional delay, I'll hand it over to Fernando.
Well, I have the mic, yeah. All right. So hello, everyone. Can everyone hear me? Yeah? OK. So let's talk about the polygamous nature of urban data sets. So recently, lots of people have been talking about big urban data, so big data related to urban environments. And what's the big deal about it? Well, cities are the locke of economic activity, and it's where 50% of our population is living right now. And this number tends to grow. So by 2050, this number will grow to 70%. So of course, with this growth comes many problems that needs to be addressed, but at the same time, are really hard to solve. So we have problems related to transportation, because you have too many people with the resource that you have. You also have problems with housing or pollution with the environment. But now, the good news is that we have the data. The data is like the light at the end of the tunnel. And we can lots of data have been collected throughout these years, and we can use this data to actually help better understand the cities. So which kind of data we are talking about here? So we are talking about data about the infrastructure of the city, for instance, subway rides or taxi trips. We are talking about, here we also have data about the environment. So a clear example of that is the weather data set. And we also have data that reflect the behavior of citizens, which is usually reflected by social media data. So to understand the city, one can understand the data exhaust from the different components of the city, and that brings a huge opportunity, which is to make cities more efficient and improve the lives of citizens. So let's take a look at some examples of questions that data scientists or even city agencies they may make while they're trying to explore this data to better understand the cities. And in this case, I will use the city of New York as an example. So the first question is related to the number of accidents, car accidents in the city. So if you have too many car accidents, a valid question would be, would a reduction in the traffic speed reduce the number of accidents? The second question is related to the struggle that New York City residents have, which is to get a taxi, to take a taxi when it's raining. And the question is, why is that so? Why is it so hard? What can we do to actually improve the taxi service in rainy days? And then finally, while they are trying to analyze, for instance, the data about taxi trips in the city throughout 2 different years, they realize that there are some drops in the number of taxi trips in some particular points. And then the question here is, why is that so? Was that a data quality problem, maybe a corruption during the data collection, or maybe there's something interesting that happened in those points that we need to look at? And if you look at those questions more carefully, you can see that they all play with interactions of different data sets. So for instance, for the first question, you have data about traffic speed, and you also have data about number of accidents. For the second question, you have the taxi data set interacting with the weather data set. And then for the third question, you have the taxi data set, which may interact with other data sets to actually explain those interesting patterns in the data. So what we see here is that those urban data interactions or these relationships between those data sets, they can actually help us better understand the cities. And by uncovering those relationships, you can also uncover the interesting, the important attributes of those data sets that can be used, for instance, to have predictive models of the different process of the city. And as a matter of fact, urban data sets, they can be very polygamous because you may have many-to-many relationships between them, so attributes from one data set interacting with many other attributes from many other data sets. So data are available, as we mentioned before, so we are probably good, right? Not exactly, because here we are talking about big data. So for instance, for NYC Open Data, which is the open data portal for urban data in New York City, we have 1,200 data sets, and this number is still growing. And the question now here is, where do we start? Which data sets we need to first analyze so that we can actually have those questions answered? And also, for NYC Open Data, again, we have more than 300 data sets that are spatio-temporal, which means that more than 300 data sets, they have spatio-temporal components, which makes the analysis a little bit more complicated. It adds a new layer of complexity, because now you need to look at perhaps different temporal slices and different spatial regions. So attributes, they may relate differently depending on time and space. And if you want to do this analysis manually, you need to have all your hypotheses beforehand and test them. So first of all, having all these hypotheses beforehand is sometimes even unfeasible because you don't even know what exactly you're looking for. And second, testing all these hypotheses manually is very time-consuming. So our goal here is then to allow the users to pose what we call relationship queries. So for instance, find all data sets related to a given data set D. So the idea then is to guide users in this data exploration process, helping them to identify those connections among disparate data, and hopefully identifying those variables that can be used to model the city. And the questions that I showed before can be easily translated to these queries. So for instance, for the first question, would the reduction in traffic speed reduce the number of accidents? We could be translated to find all relationships between collisions and traffic speed data sets. And for the second question, why the number of taxi trips is too low, could be translated to find all data sets related to the taxi data set. And you can see that this can help with hypothesis testing because you have a hypothesis, in this case, that the number of accidents and the speed limit are related, and you simply want to test it to check if it's true. Or it may also help you with hypothesis generation because you don't know why the number of taxi trips is too low, but you want to generate a hypothesis that may explain that behavior. But of course, allowing users to pose those types of queries comes with challenges. So the first one is related to the definition of the relationship itself. How can we actually define a relationship between data sets? So let's go back to our tax trips data set. So you can see that there are some of these points in time where you have a low number of tax trips. And as a matter of fact, if you take a look at the wind speed data, you see that the points where you have abnormally high wind speeds is where you have a low number of taxi trips. And in this case, this is related to the hurricanes that hit New York City in 2011, 2012. So if you look at those two data, you can see that they are not actually much related if you look at the entirety of the data. And it is true that the wind will not influence that much the number of taxis in the city, but only when you look at those interesting features, at those interesting happenings, is that when you see the relationship. It's where the relationship becomes visible. So what we are interested here is on relationships between those interesting features of the data. And also because we're talking about spatial-temporal data sets here, for instance, if we have a car accident in one neighborhood, this probably won't affect the traffic in the neighborhood that is too far away. So you also need to take into account both time and space. And what happens is that the conventional techniques to find correlations between data sets, they cannot find these relationships because first they look at the entire data, and second, they don't take into account both time and space. The second challenge is related to the large data complexity, big urban data. So again, here we're talking about many, many data sets, and the data is available at multiple spatial-temporal resolutions, and also the relationships can be between any of the attributes. And these data sets, they may have many attributes. So as an example, for NYC Open Data, we have an average of 8 attributes per data set. And some data sets, like the weather data set, has more than 200 attributes. So in that case, you have a combinatorially large number of relationships to evaluate. So only for NYC Open Data, for a single spatial temporal resolution, you have approximately 2.4 million relationships to evaluate. So looking for meaningful relationship is like finding a needle in a haystack. So our approach then, which is called data polygamy, has the goal to help the user in generating those hypotheses and testing them automatically in an efficient and scalable way. And we address those challenges in 2 ways. So for the first challenge, we use what we define as topology-based relationships. And for the second challenge, we have our implementation using MapReduce. So now I will pass the torch to Harish, and he will talk in more details about topology-based relationships, and then I'll come back to talk about implementation.
Thanks, Fernando. So let me now briefly introduce the mathematical concepts behind our technique. And primarily, what we're interested in is to identify these relationships based on what is known as topological features. So what do I mean by topological features? Let's again consider our 2 favorite data sets, which is the taxi data and the weather data set, right? So the kind of features we are interested in here correspond to these deep valleys, or they correspond to these peaks.
Press harder.
Okay. Right? And these are what are mathematically captured as critical points. And so an advantage of using computational topology to identify this is that techniques from topology naturally identifies these critical points of the data. So in order to do that, let's formalize this further. So how do you represent this data, and how do you go about computing these features? So the data is represented by what is called as scalar functions. And a scalar function is essentially a map that maps points in space and time to a real value, right? So let me again give you a concrete example. So in this particular case, we have number of taxi trips in New York City over time. So the city, or the spatial component here, is essentially a single point, and so you have a time series. And for each point in time, you have a value, right? Instead, I can increase the dimension over here and say, let's look at 2D slices of the data over time. So here I'm showing 2 different examples at different resolutions. The first one is essentially where we divide Manhattan, in this case, into a high-resolution grid. And for each cell of the grid, we compute the number of taxis in that cell, right? And the color map here basically says if there's a high density of taxis, then you have a bright red. And if there's a low density of taxis, it becomes white. The second example over here, the resolution, is basically the neighborhood resolution, where we divide Manhattan into its set of neighborhoods. And we again count the density of taxis within each neighborhood. So when you look at 2D slices, you can actually have each slice in multiple resolutions, and then you can again have it over different resolutions, right? So now, given these scalar functions, how do we go about computing the topological features? So we define a topological feature to be a neighborhood of critical points. And so let's visualize the data or the scalar function as a terrain instead of a color map like I showed before. So you can consider the space over here as set of all points in the city. And instead of giving a color to a point, I give a height to that particular point. So here, the scalar function is represented as a terrain. So the kind of features we are interested in, or the kind of critical points we are interested in, is basically the maxima, which correspond to the peaks of the function, and the set of minima, which correspond to the valleys, right? And the neighborhood of these critical points is essentially defined using a threshold. So what do I mean by this? Let's fix a particular threshold. So in this case, we have a function value. And let's look at all points above this threshold, right? So here we see there are 2 features, 2 components of the features corresponding to 2 of the maxima of the function. So this is what we define as the neighborhood of these critical points. And in this particular case, since we are looking at maxima, we call them the positive features. Similarly, with respect to the minima or the valleys, you can again have a threshold, and you can look at all points corresponding that have function value less than this threshold. So this gives us the neighborhood of the set of minima, and in this case, there's just one component for it, and we call this as negative features, right? And so given a data set and a data representation as a set of, the space is basically a set of spatio-temporal points, these features are going to be a subset of these points. So they are also going to be a set of spatio-temporal points. So how is such a definition basically going to help you in identifying interesting features? Let's look at a concrete example. So here what we have is, again, the set of taxi trips. So for the taxi data essentially consists of all trips that happened in Manhattan or in New York City. And for each trip, we have the pickup location and the drop-off location, which is provided as GPS coordinates, right? And over time. And here, what we are showing is basically a set of all trips that happened in this neighborhood of Manhattan between 8 a.m. and 9 a.m. on May 1st, 2011. Why is this interesting? So if you look at this particular region, so this corresponds to 6th Avenue in Manhattan, you can see that there are no pickups or drop-offs in that region. And the reason for that is the whole avenue over there is blocked to traffic because there was a 5-borough bike tour that happened during that time, right? So now if we use an appropriate threshold and look at the negative features, we actually find the exact path taken by the bike tour as a feature, as a negative feature of this data, right? And so if you notice, we don't have to predefine the shape of features that are interesting. So typically, a lot of techniques usually assume that the shape is, say, a square or a rectangle or elliptical. But in this case, you can actually have arbitrary shapes by just defining an appropriate threshold to the data, right? So yes, having such a definition is really helpful, but how do you efficiently compute this? So to do that, we use an index which is called as the merge tree. So to explain what this index is and how we can efficiently compute these features, let's again look at this example of the terrain. And let's start with a threshold that is higher than the global maximum value, right? So in this case, there are no features. The features are empty. Now, if I decrease the threshold a little bit, you can see that there is just one component of the topological feature corresponding to the global maximum. If I decrease the threshold further, you can see that at some point, the other peak also becomes a topological feature, and now you have two components. If I decrease it even more, what we have is three components, and as we keep decreasing, at some point, these different components merge together, and finally, once it goes below the global minimum, we have the entire data as a single component of the topological feature, right? And as you notice, as we keep decreasing this threshold, you see we have a tree that captures basically the evolution of the topological features. And in particular, the leaves of this tree correspond, the leaf nodes of this tree corresponds to the set of maxima and the set of minima, and the internal nodes are what other types of critical points, which are called saddle points, right? And so this merge tree kind of abstracts the shape or the topology of the input data, and it gives us a data dimension independent way of analyzing the data, right? And one of the main advantages of using this merge tree is you can actually compute the merge tree efficiently in O of n log n time, where n is the size of the scalar function. So even if your data is extremely large, for example, the taxi data that we use, we have data corresponding to 5 years, which has over 868 billion trips, right? And even though it is so large, once you convert it into scalar functions over space and time based on the neighborhood, it's going to become a much smaller sized function, and you can just compute it efficiently in O of n log n time. And so now that we have this merge tree index, how do you go about computing the features? So to do that, given a threshold, all we need to do is basically start from the critical points that are above this threshold in the merge tree, and we need to keep traversing down the merge tree. So, and we just stop when we hit this threshold. So basically, the plane that is the threshold, which is a plane in the actual data, now becomes just a single line in the merge tree, and you just traverse down it. So basically, what we are doing is we hit each point of the feature exactly once, and we don't touch any other feature, right? So, or in other words, what we have is an output-sensitive algorithm to compute these features, which basically says that no other algorithm can perform better than what we are performing. This is the best that you can do, right? So now we know how to efficiently compute these features. So far, what we have mentioned is we have defined topological features based on a threshold, and given a threshold, we know how to compute these features. But how do you go about finding good thresholds? That's a question, right? So for example, when we used the taxi data earlier, we actually found the path. How do you get that threshold in a nice way? And of course, users or domain experts who know the data can manually give thresholds, but given over 1,000 data sets, each with 8 attributes per data set, which essentially gives us something like 8,000 different functions in one resolution, how you just cannot manually provide thresholds for every data set, right? So in order to do that, we compute these thresholds in a pure data-driven approach. And to do that, we use this notion called topological persistence. So what do I mean by topological persistence? So if you recall, when I kept changing the threshold values, at some points there were new components being created, and at some points the components merged, right? And so if you think of a component being created, you can think of it as a component being born. And when two components merge, you can think of the smaller component as being destroyed, right? So for each component, you have a function value where it is created or where it is born, and a function value when it actually dies or when it's destroyed. So you can define some sort of a lifetime for each of these topological features. And this lifetime is essentially what is called as topological persistence. So intuitively, when you represent the data as a terrain, the topological persistence corresponds to the height of each of the peaks. So a high persistent feature would basically have will be really tall, whereas a low persistence feature would be really short, right? And the other advantage is, again, you don't have to look at the data again. Once we have the merge tree, the topological persistence can be efficiently computed using the merge tree itself. So we have this abstract tree representation, which is much smaller than the original data. You can just use it to compute these thresholds, and then you can again use this merge tree index again, using these thresholds to compute the required features. Right. So I still haven't finished how to compute the thresholds based on persistence. And so to do that, we use what we are interested in is the set of high persistent peaks or high persistent valleys, right? So to do that, we use what is called as a persistence diagram. And this is essentially a scatter plot, which plots the birth versus death of each of the features. So here again, we are using the taxi data, and this is the persistence diagram for all the features of the taxi data, right? And so here you have the x-axis, which is when it was born, and the y-axis is when it is destroyed. And so the persistence value is essentially the height above the x equal to y plane. And if you notice closely, the set of high persistent features actually form a separate cluster over here. They are separate from the all the other features. And this is not just for this data. This is common across several data sets. And in fact, the persistence diagram is commonly used as a visual aid for users to identify good thresholds and interesting features of data in several applications, including scientific simulations and climate simulations and so on, right? So we basically use this insight to automatically compute the threshold by identifying this high density cluster from the persistence diagram. And another advantage is that you can theoretically prove that the persistence diagram is robust to noise. So basically, you have, say you have clean data, and then you have the same data, but with addition of noise. You can actually prove that the persistence diagram doesn't change beyond a particular distance, right? So there is no change, and it's really robust to noise. So now we have ways to compute different features of multiple scalar functions, which is basically each attribute of all the data sets, right? So how do we use this to evaluate the relationships? How do we find these relationships? So to do that, we first define relationships between individual features. We first say when features are related. So to explain that, let's again look at our favorite terrain. So this is, consider this as one scalar function. And then next, let's look at a different terrain which has a single peak, and this is the second function, right? So if you look at the set of features over here, you see that the first function has 2 positive features and 1 negative feature, while the second function has 1 positive feature. But in particular, this positive feature is in the same spatio-temporal location as the taller peak in the first function. So in such a case, we say that these 2 features are related. And in particular, since a positive feature is related to another positive feature, we say there is a positive relationship. Now let's consider a different pair of functions. So even here, the second function still has just a single feature, but it has a positive feature, right? And here you see that a positive feature is actually related to a negative feature. So in this case, we say there is a negative relationship between the feature. So we basically use this definition of relationship between features to quantify relationship between 2 functions or 2 data sets. So to do that, we define 2 different measures. The first one is called the relationship score, which captures how the features are related, right? So in this case, whenever there is a negative feature in one function, there is a positive feature in the other function. So we say that this function is negatively related. And therefore, the relationship score would be negative in this sense, below 0, right? But this is just not enough because it doesn't say how frequently the different features are related. So if you look at this example, you see that only one of the features of the 3 in the first function is related to a feature in the second function, right? So we need to quantify this. To do that, we need to say how often the functions are related. And we do this using a relationship strength measure. And in this particular case, we say that there is a weak relationship between the 2 functions. So if there was another function wherein such that it had, say, 3 features and all of them were related, then we would say there is a strong relationship, right? And in addition to this, we also perform a set of Monte Carlo significant tests to filter out potentially coincidental relationships. And as we'll show later, the user can specify the p-value of interest to filter out relationships. So if you noticed one thing, the way we have defined our topology-based relationships, so whether we use data that is like a 1-dimensional data, or whether we use data that is 3-dimensional in this case, that is 2D space over time, all we work is with the merge tree. And the same algorithm, the same code is going to work on data in any dimension because we just use a merge tree and then the persistence to compute different thresholds and identify these features. So essentially, we have a dimension agnostic technique to compute these relationships. So to recap, using computational topology to identify relationships, they naturally captures the features of interest in the data, which can have arbitrary shapes. And they are really efficient, robust to noise, and it's independent of the dimension of the data. So now that we have a solid mathematical framework to do this, let's see how we go about implementing it.
All right, thanks, Harish. Let's do one, okay. All right, so let's talk more details about the implementation of the framework. So all the scalar functions that are generated from the data, they are considered to be independent from each other. And even the relationships, when you have all your hypotheses of the relationships generated, all these relationships, they are also considered assumed to be independent from each other. So what happens here is that all our steps to compute and to identify features and even to evaluate relationships, they are embarrassingly parallel. So we can use MapReduce to implement our framework. And this also helps with efficiency because we have a large collections of data sets with multiple attributes. And so this also helps in making it very scalable. So this is what the framework looks like. So we have 3 main steps, and each of these steps is a MapReduce job. It's represented by a MapReduce job. So the first step, which is called dataset transformation, takes all the data sets, all the attributes, and creates a consistent representation of the data. So as Harish mentioned, the consistent representation of the data, in this case, are the scalar functions. In particular, for this implementation, we use 2 different types of scalar function: count and attribute. So the count function basically captures the activity of an entity corresponding to the data. So for instance, we could have a density function, the number of text strips over space and time. And we could also have a unique function, number of unique taxes based on text license or text medallion over space and time. We also have the attribute functions, and the attribute functions, they basically capture the variation of an attribute. So in this example, we have average text fare over space and time. And it's important to note here that we compute these functions at all possible spatial-temporal resolutions. So suppose you have some data where the spatial component is in GPS. So the GPS can be then translated to a high-resolution grid, or maybe the points can be mapped to different neighborhoods, or you can consider the entire city as a whole. And if the temporal component is in second, you can also translate it to hour, day, week, month, and so on. So we compute all these possible combinations of spatial-temporal resolutions because, as we are going to see through an example, a relationship they may be visible in one resolution, but it may not be visible in another resolution. And it's also important to note that, of course, in this framework, we only have these implementations of the scalar functions, but it is quite straightforward to add other functions to the framework. For instance, one function that we really plan to implement inside the framework is the gradient function, so that you can try to capture the increase or decrease of a certain characteristic in the attribute. And with respect to the MapReduce job, in the map phase here, what happens is that all the data points, they are mapped to these different spatial-temporal resolutions. And then in the reduce phase, the data is aggregated using the scalar functions for each of these resolutions. So the second step is feature identification. It's where all the features are computed and identified. And here, the map phase for each of the data sets, scalar functions are taken individually. What do I mean by that? Well, if we talk about key value pairs, in the dataset transformation, the dataset is considered as a whole. So the value is basically a list with all the attributes or scalar functions corresponding to that dataset. And what happens in the map phase of the feature identification is that we split this into different key value pairs, where each of these pairs corresponds to a different scalar function or attribute. Because as I mentioned before, they are considered to be independent from each other. And then in the reduce phase for each of these functions, the merge tree index is created, and the features are identified for all the possible resolutions. And here, the beauty of the merge tree is that you can compute the merge tree once, and then you can have different thresholds, and you can also always use the same merge tree with different thresholds to identify your features. So as soon as we construct the merge tree for the first time for a particular function, we save that. And then whenever the user needs to go back to the feature identification to use a different threshold, perhaps, to identify features, the same merge tree can be used, and this does not need to be computed again. And then finally, the last step is the relationship evaluation, which is where the relationship is identified and evaluated. So this is where the user is, where the user can pose relationship queries. So again, the relationship query is in the form of find all data sets related to data set D satisfying clause. So what happens is that when the user runs this query, only the statistically significant relationships are returned, which significantly reduce the number of relationships that the user needs to analyze, thus better guiding the user in the data exploration process. And if you note, in the query, we have a clause where the users can use to actually filter the relationships based on relationship score and strength, because these are like quantitative metrics, so they can use a specific threshold for the score and the strength, and you can also choose a different p-value for the significance tests. And in terms of the map-reduce job, in the map phase, all the possible combinations of scalar functions are considered based on the query. So basically, all the possible relationships are generated based on the query. And then on the reduce phase, each of these relationships is evaluated, and it's also in the reduce phase where the statistical test is done. And some additional information, we implement this using Apache MapReduce. We use HDFS as a distributed file system. It proved very efficient for us to use compression in the map outputs, because the mappers, they produce a lot of data because we have a lot of scalar functions to compute. And so we used a few different compressions, and that proved to be very efficient. And also the framework runs on AWS. So then, after we implemented this framework, of course, we ran a few experiments to test the framework for efficiency and also for to see if it's useful. So the first set of experiments is related to performance evaluation. So our goal here is really to check for efficiency, scalability, and robustness. So for that, we use 300 spatial-temporal data sets from NYC Open Data, which is very reasonable because it has a large data complexity, because again, as you may remember, each of these data sets has an average of 8 attributes. So it creates a large a possible number of relationships. And the hardware that we use, so we have our own Hadoop cluster at NYU, which we use for most of the experiments. And this cluster has 20 compute nodes. But we also used Amazon EMR for the scalability tests. And the reason is because with Amazon EMR, it is incredibly easy to create different clusters configurations so that we can test for scalability. So here are a few results from our framework in terms of performance. So the first one is that it takes around 200 minutes to compute all the scalar functions and features, and also to evaluate the relationships for NYC Open Data, which is a very reasonable time considering the large data complexity. Also, using the significance test, we can decrease in around 99% on the number of output relationships. So this indeed better guides the user in finding potentially meaningful relationships. And also, the framework can evaluate more than 10K relationships per minute. So this plot, for instance, on the x-axis, you can see a number of varying data sets. And then on the y-axis, you have the rate. And then you have 10K, and then it goes up to 15K relationships. Also, we incrementally added noise to the data. And we could also always find the same relationships. So the approach is robust to noise, and this is thanks to topology, because as Harish mentioned, the persistence values, they are very robust. And also the approach is scalable. So this is the experiment that we ran on Amazon EMR. So we use different types of cluster configurations with 2 nodes, with 4 nodes, with 8 nodes, and finally with 16 nodes. So the first step, which is the data set transformation, where we compute all the scalar functions, it has a very nice speed up. The 2 last steps achieve the lower speed up, and the reason here is because we have a few straggler reducers that are working on high resolution data. So high resolution data means that we have much more data to process, so they keep processing the data while the other reducers are already done. So finally, we've seen that the approach is efficient, that the framework is scalable, but now is it useful? Can we actually find interesting non-trivial relationships? So this is the goal of our second set of experiments, which is more of a qualitative evaluation. And for that, we manually selected 9 data sets from different NYC agencies, which are data sets that we are more familiar with, so that we could try to better understand some of these relationships. So let's take a look at some of these interesting relationships. So let's go back to our first question, which is, would the reduction in traffic speed reduce the number of accidents? Which can be translated to the query, find all relationships between collisions and traffic data sets. So for this query, we found a relationship, a positive relationship between the number of collisions and the speed, which indeed indicates that the speed is the speed limit in the city is positively related to the number of collisions in the city. But we also found another relationship, which is a positive relationship between the number of persons killed in those accidents and the speed, which indicates that reducing the speed limit in the city may also help in reducing the number of fatalities in the city, in car accidents. And as a matter of fact, the city of New York in 2014 decreased the speed limit to 25 miles per hour to reduce the number of traffic deaths, which is consistent with our data, which goes until 2014. So for the second question, why is it so hard to find a taxi when it's raining, which translates to the query, find all relationships between taxi and weather data sets. So the first relationship that we find is a negative relationship between the number of taxis and average precipitation, which does indicate that it is indeed hard to find a taxi when it's raining. So it's not an urban legend. But this still doesn't explain why is that so. So there is a long-standing hypothesis in the city that taxi drivers are target owners. So basically, they have their daily income goal, and when they reach that goal, they simply go home and they stop working. And of course, in rainy days, the demand is higher, so it's harder to find a taxi because they are all gone. And the question here is, given this hypothesis, can we actually find a relationship that indicates that this hypothesis is true? As a matter of fact, yes. So we found a strong positive relationship between precipitation and average fare, which does indicate that this hypothesis is true. And what's interesting about this is that this hypothesis was recently refuted in a recent study. And the reason is twofold. So first, in this study, the authors, they, instead of using the amount of rainfall, the amount of precipitation, they only used binary values indicating whether it rained or not. And second, and most importantly, they used the entire data into account. So basically, periods of time with sparse rainfall were considered to be equivalent to periods of time with heavy rainfall. So this indicates that we need to look at these interesting relationships, because some of these relationships, they only become visible when you're looking at those interesting features and not when you're looking at the entire data. So for the third question, why the number of taxi trips is too low, which translates to find all data sets related to the taxi data set. So we've seen already one of the relationships that explains this, which is the negative relationship between number of taxis and wind speed, which is related to the hurricanes that hit the city. But you still have other points where the number of taxi trips is too low. And this can be explained with another relationship, which is a negative relationship between number of taxis and average precipitation. When there's too much rain, also it's hard to find a taxi. So you can see that for a single question, so you have a single question can be answered by more than one relationship, and they actually complement the answer for this question. And by digging into this relationship, analyzing it further, you can see exactly where are the points where these relationships are visible. And finally, this is a very interesting relationship that we also found, which is between the city bike data and weather data sets. So city bike is the public bike system in New York City, for those who don't know. And we found this negative relationship between snow precipitation and active city bike stations. So meaning that the higher the snow precipitation, some of these stations from city bike, they are less frequently used than others. So we believe that this is related to two things. One, obviously, when it's snowing, people use bikes less frequently. And second, some of these stations, they are cleared more frequently than others because they're simply in more popular places or even more expensive places, right? And what's interesting about this relationship as well is that we could find it in the day city resolution, but we could not find it in the hour city resolution. And the reason is this relationship is only visible when you have is no accumulation. After you see there's no accumulation, then you see this relationship. And if you are working on an hourly time resolution, you cannot see this no accumulation. But when you go to the daily resolution, then you can see this accumulation happening. So this shows that it is really important that you look at relationships at these different spatial-temporal resolutions. And of course, we found many other relationships. So for this collection of data set that we found approximately 100 significant relationships per resolution. We manually looked at some of these relationships, and we found over 35 that were interesting. But of course, we do need domain experts to look at the other relationships so that we can try to better understand their implications and the reasons behind those relationships. And in our analysis, we also found that the weather data set is the most polygamous data set, meaning that its attributes, they relate to almost every other attribute in the other data sets. So to conclude, we have presented data polygamy with the goal of discovering and exploring relationships in large collections of data set. So we use the concept of topology-based relationships because it considers relationships between salient features of the data, and also because it takes both time and space into account. The framework was implemented using MapReduce, which proved to be very efficient and scalable. And we also could find some interesting and even non-trivial relationships in our framework. But querying for relationships is just the beginning. And these are some of the lessons that we learned while working in this project. So the first one is it's really hard to evaluate this framework because we don't have ground truth data. So we do need real use cases from domain experts or perhaps a benchmark that can generate some data with relationships so that we can evaluate better our framework. And the second one is that even though we have the significance test that significantly reduce the number of output relationships, depending on the size of your collection of data sets, you can still have too many relationships to look at. So here we need better tools and techniques that help the user, better guide the user in exploring and analyzing those relationships. And so that's it. In our GitHub page, you can find some code, data, and experiments. And we also have a paper published this year at SIGMOD. And you can have more details about the approach in the paper as well. And thank you.